My name is Nurul Atira binti Abdullah and my metric number is 293901.
My name is Nurfatia binti Ismail. My metric number is 292013.
My name is Siti Nobatrisha binti Abdul Halim and my number metric is 292828. Introduction. Relations are a fundamental concept in mathematics and discrete structure, forming the basic for understanding how elements in a set interact with one another. A relation on a set is defined a subset of the citation product of the set with itself. Understanding the properties of relation, whether they are reflexive, symmetric, asymmetric, antisymmetric, or transitive, it's a crucial in a various fields, including computer science, database design, and logic. This study dives into the characteristics of relation to determine how these properties manifest, emphasizing their importance in both theoretical and practical application.
Objectives. First, to define the properties of a relation: reflexive, symmetric, unsymmetric, antisymmetric, and transitive. Second, to develop a symmetric approach to determine whether a given relation satisfies their properties. Third, to apply this understanding to real-world examples and scenarios where such properties are crucial. And lastly, to enhance logical reasoning and analytical skill by studying the structural properties of relations.
Next, I will move to another part, which is definition of relation. Firstly is a reflexive relation. Every element in the set must relate to itself. In the example, each number in the set A has a corresponding pair where both elements are the same, such as 1, 1. Next, the second relation is irreflexive. Unlike reflexive relation, irreflexive ones ensure that no element related to itself. Here we see that the pairs like 1, 1 and or 2, 2 are missing, making the relation irreflexive. Next is a symmetric relation. If one element is related to another, the reverse must also hold true. For instance, if 1, 2 is in the relation, then 2, 1 must also be included. And then another relation is asymmetric relations, which is a symmetric relation prohibit any element from having a mutual connection. Here, while 1, 2 exists, the reverse 2, 1 does not, for ensuring the asymmetry. The last one is transitive relation. In transitive relations, if an element is connected through another, they are directly related. For example, since 1, 2 and 2, 3 exist, 1, 3 must also be present.
Hi, Assalamualaikum. My name is Izzat Insyara binti Zamri with metric number 286587. Now I will explain about our source code and the interface that our group create using Visual Code Studio. Okay, for this code, the set input split into an array by commas, and any extra spaces are trimmed. For the relation input, we use a regular expression to extract pairs in the format in bracket A, B, and convert them into nested arrays of 2 each elements. Next, we check if the relation is reflective. Reflectivity requires every element in the set to relate to itself. Here's the logic. We use filters to find the element in the set that do not have a corresponding pair, like in bracket A in the relation. If there are no missing pairs, the relation is reflective. And now let's move to symmetry. For symmetry, we ensure that for every pair in bracket A, B in the relation are reverse pair. In bracket B, A also exists. Here's the code. We iterate through the relation pairs and use sum to check if the reverse pair exists. If any pair is missing its reverse, the relation is not symmetric. Now let's move to the asymmetric part. Asymmetry is the opposite of symmetry. It means there no pair in bracket AB has its reverse in bracket BA unless A equal to B. Here's how it's implemented. We check if there are any pairs in the relation that violate the asymmetric condition. If none are found, the relation is asymmetric. Antisymmetry is a slightly relaxed condition compared to asymmetry. It allows in bracket AB and E bracket BA only if A equal to B. Here's the code. We filter pairs that violate the antisymmetric condition and count them. If the count is 0, the relation is antisymmetric. For transitivity, if in bracket AB and in bracket BC exist, then in bracket AC must also exist. Here's the code to verify this. We use nested loops to check all combination of pairs in bracket AB and in bracket BC. If in bracket AC is missing, it is added to the list of valuations. After processing all the properties, we generate a dynamic table to display the results. Here's how the results are created. This program ensures an accurate and user-friendly evaluation of relation properties. It uses dynamic programming techniques and provides detailed feedback to the user. This interface for the relation property checker allows users to input a set of elements and their relations. The first field accepts the set, for example, in bracket ABC, and the second takes relation as pairs, for a bracket AA and in bracket BC. Please hold the text guides input formatting. Clicking the green check properties button processes the inputs to analyze properties like reflexivity, symmetry, and transitivity with result displayed below. The design is clean, user-friendly, and easy to navigate. And now let's move to the last part of the interface. The top section contains the inputs, the set in bracket ABC, and the relation defined as pairs in bracket AB and in bracket BC. After clicking the check properties button, the results are displayed below under the relation properties heading in a table format. The table has 3 columns, which is property, result, and justification. Each row represents a specific properties of the relation. For reflective, the result is no because some element of the set, for example, in bracket AA, in bracket BB, and in bracket CC are not included in the relation as shown in the justification. For symmetric, the result is no because certain symmetric pairs, for example, in bracket BA and in bracket CB are missing from the relation. For asymmetric, the result is yes because no pairs in bracket AB exist with its reverse in bracket BA. And for antisymmetric, the result is yes because all of pairs in bracket AB and in bracket BA that exist, it ensures A equal to B. For transitive, the result is no because the relation violates transitivity. For example, in bracket AB and in bracket BC exists, but in bracket AC is missing. As noted in the justification, the table is well structured and the green headers highlight the columns for easy readability. This provides users with a clear, detailed analysis of the input relations properties.
In conclusion, the project relation property checker is a simple and user friendly to design to help user understand and verify the properties of relation, such as reflexivity, symmetry, and transitivity. It's features a clean and organized interface, making it easy for users to input set and check their relation properties efficiently. And this tool also is a practical and accessible solution for learning and exploring relation properties in mathematics or computer science.